All right, everybody, welcome in. So we'll be continuing along with our discussion. So just to kind of get everyone back up to date again. So today's the 18th, Tuesday. So you have chapter 5 due on Monday. That's a very hefty chapter. Unfortunately, I can't give you any more time because as you see, shortly thereafter, you have chapter 6 due. And I can't push chapter 6 back any because the class will be over. So just to kind of reiterate a few things, the due dates where we're now at are pretty much the due dates. I can't move things back any further because the class ends next week. So make sure that you're getting caught up. I can't extend the homework. I can't do any of that because I have to try to get grades in immediately. So just be on top of it. The homework that you get done is the homework that you'll get done. So try to make sure that's as much as you possibly can. Get all those homework points that you can. So we'll be talking about, my goal is to talk about 5.2 and 5.3 today. And then we can talk about 5.4 and 5.5 on Thursday. And then next week we'll tackle chapter 6. Remember, next week you have to take the final exam sometime next week. I mean, technically you could take it this week, but you wouldn't really want to because you don't know all the stuff yet. So get your testing center appointment set up. You're gonna need it. If you haven't already, hopefully most of you have. So get that appointment set up. You do not need a Scantron. This is not a multiple choice test. This will be a traditional written test. You'll show me work. I'll give you partial credit, all that kind of stuff. It will cover up to the beginnings of chapter 6, but I'm not going to put all of chapter 6 on there because some of it you'll have been learning like the day before. That's kind of rough to test someone on something they learned the day before. But the early parts of chapter 6 will end up on the test. I plan to post a practice test for you on Wednesday. So I guess, is that tomorrow? Yeah, I guess that's tomorrow. So that should show up inside of Canvas tomorrow. That gives you, a number of days that you can work on the practice test. You can take it to the testing center and get help with it. You can form study groups and talk to each other about it and work together. So that's where we're going with that. Make sure so watch the calendars, watch those due dates and XYZ homework. Make sure you're getting that stuff completed because when I cut it off, I got to cut it off. Practice exam Wednesday. Make sure you're all set to take your exam next week. Yeah, I think that's where we're at with stuff. So I think that's hopefully getting everybody kind of up to speed there. So we're diving into two big topics. Again, I know chapter 5 is weird because this is always the case in a calculus class like this. Chapter 5 just seems like all these different things that have nothing to do with each other. And then all of a sudden at the end, you get the fundamental theorem of calculus, which just sort of fits everything together, and you realize it was all connected in the first place. But it can be a little bit disorienting as you're working through this chapter. So we're going to start off by talking about 5.2, which is integration by substitution, which is, I'm oversimplifying a little bit, but it's basically doing the chain rule backwards. So remember when we talked about 5.1, we were talking about anti-differentiation. That's where you sort of reverse engineer your derivatives and you work through them backwards. So instead of having a function and finding its derivative, you have a function and you find the function it's the derivative of, right? So you're working the other direction. Well, some problems get really tricky, especially if you had to use the chain rule to take that derivative. It's extra complicated to sort of reverse engineer your way through, and that's what substitution does for us. So 5.2 you can basically think of as anti-differentiation for the chain rule. Again, I'm a little bit oversimplifying, but that's kind of the idea of what we're doing there. And then 5.3, the definite integral, is going to seem very strange, like it just came out of nowhere and has nothing to do with anything we've done. But as you'll find, it does. It is related. Okay, it does have to do with it. So let's take a look at the book and work our way through some things. Okay, so we've got this notation. Hopefully will look familiar to you if you've already started working on chapter 5. That's our integral symbol, right? And for us at the moment, when we see this, this means find the antiderivative of. this function right here. Find the function that this is the derivative of. And now these probably look more complicated. For those of you who have already done 5.1, you're probably looking at these problems and going, whoa, those seem complicated compared to what we just did on the homework, and they are. They're not quite as bad as they look. Once you understand substitution, these problems will become much easier for you. But it's a little tricky at first, like wrapping your brain around something like this and trying to figure out what's this the derivative of. But once you get substitution and once you've done a few of these, you start to recognize some patterns and you go, oh, this problem right here looks really scary. It's actually not bad. Once you see the pattern and you see, like, you learn how to look at these, you go, nope, I know exactly what to do for this problem. So don't let these intimidate you. You'll be fine. But it does take some setup to figure out how to do that. Yeah, thanks. We'll get to roll call in a little bit. Thanks for reminding me. I almost forgot in my morning class, so thanks for, I'll put this here so I remember to do the roll call there. Yeah, so we'll talk about various of these. Right, so let's take a look in the book. Okay, so let's first, before we get into that, let's just sort of remind ourselves what we're talking about with antiderivatives and that whole thing. So remember, we can start with a function. So let's just say, like here, we start with the function 5x squared minus 4x plus 1. So we've got that function there. So we know that the derivative of that, right? Hopefully everyone's real comfortable with that by now. The derivative of that would be 10x minus 4, right? So we have this function f, and then we have f prime of x, which is the derivative. So we would also say that this function f of x is the antiderivative of f prime of x, right? So you can kind of think of it as a direction. As we move down, we're taking the derivative. As we go up, we're taking the antiderivative. It just depends which direction you're heading when you're dealing with those functions. So as we move down, we're taking the derivative. As we move up, it's the antiderivative, except there's this one little caveat. We have to be careful because this function actually has lots of antiderivatives. So remember, there's that plus c we have to add on to the end. So be aware of that. Like, remember that, because that's a place where students miss points. They'll just forget to do it on a test. But the problem is if you forget to do it like 10 times, that's 10 points right there. It's kind of brutal, but each time you forget it, it sort of makes a difference. So that's just a real quick recap of what we did last time. You have a function, you can take its derivative. If you go the other direction, reverse engineer that derivative, you're taking the antiderivative, except in that case you have, like, instead of a plus 1 here, we'd have a plus c on the end of that thing, right? So with that said, let's take a slightly more complicated derivative. Right, so you could kind of see, some of you are getting the hang of it with these polynomials. It's not too bad to reverse engineer your derivative and start to think about it as going backwards. When we take the derivative, you multiply by the exponent, decrease the exponent by 1. So we talked about the shoes and socks principle, which says you switch the steps and you switch the order of the steps, and then you switch each step. So instead of when they take the derivative, you multiply by the exponent and add and then subtract 1 from the exponent. To do the opposite, you add 1 to the exponent and then divide by that new exponent, right? So that gets a little bit trickier when we had to deal with the chain rule. So let's remember how the chain rule works. So let's say we've got a function g of x. And this is equal to, say, 2x squared minus 5x x plus 1, all raised to the 7th power. That is definitely some algebra that I wouldn't want to work out, right? I don't want to sit there and figure out what 2x cubed minus 5x plus 1 to the 7th is by like doing that multiplication, right? And we wouldn't want that giant, enormous polynomial anyways. So we want to be able to find the derivative of this. We called that the chain rule. Okay. So that means that g prime of x is equal to, okay, so remember we take the derivative with respect to the outer function, so 7, leaving the inner function the same, decrease the exponent by 1, and that's where sometimes people stop, but you have to remember the chain rule piece. We have to multiply by the derivative of the inner function, which in this case would be 6x minus 5. Hopefully everything I've just gone through is review for you and you're very comfortable with that, because you're going to need it to be, because we're going to start putting these pieces together. But you could imagine like this problem up here, working backwards to the antiderivative, not too challenging. But what if someone just handed you this g prime and said, okay, figure out what it's the derivative of? It's starting to look kind of a mess. It's starting to look kind of complicated, right? So you have to kind of look at it and go, how would I work backwards through a chain rule? And how do you even recognize that a chain rule was used in the problem? Well, one of the things you're going to be looking for in these problems today is the existence of a function and its derivative. So do you see how we're given in this g prime? Imagine that's all we had. Notice how we have a function here, 2x cubed minus 5x plus 1, and we also have its derivative. That's kind of the fingerprint of the chain rule. If you see a function and its derivative, that's a clue that the chain rule was used, right? So whenever you see like something that looks really complicated, look for that. Look for a function occurring and its derivative, and then ask yourself, could that have been the result of a chain rule? And if the answer is yes, then you should use substitution, which is what we're going to talk about today. So that's kind of my setup for the problem we're looking at. So integration by substitution. One of the things we're going to do, it's sometimes called substitution. You'll also hear people refer to it as U substitution, because U is oftentimes the letter that we use to make the substitution. But a lot of times what happens is when you look at a problem, it can be very complicated in the variable x. Like it's just kind of, your brain gets overwhelmed. So one of the things we do is we substitute in a new variable in a way that simplifies the problem and makes it look a lot easier to deal with. And then your brain goes, oh, now I know what rule I'm supposed to use. Rather than all these complicated x's and powers of x, you put it in terms of u, it looks a little simpler, and you go, oh, that looks like maybe the chain rule was used on a, whatever, a product or something, right? And you can sort of figure out where it came from. So, let's do this one. So I'll do example 1 and we'll walk through it. So let's go to here. So basically they're asking us to evaluate. So find the antiderivative of (12x plus 4 over 6x squared plus 4x plus 1. Now, you'll see this in different forms, right? I'm writing it as find the derivative, or find the antiderivative. We don't need all this room here. Okay, so find the antiderivative of 12x plus 4 over 6x squared plus 4x plus 1. It also can be written this way. evaluate the integral of 12x plus 4 over 6x squared plus 4x plus 1 dx. Those are the same problem, just written in a different way. So you want to make sure you're comfortable with recognizing the two different ways that that problem is oftentimes written, okay? Sometimes, like, they'll do this, except instead of saying find the antiderivative, they'll say find capital F of x when this is equal to lower f of x. It's all just different ways of asking the same problem. So what we want to do is first recognize what I talked about a moment ago. Do you see how in this problem we see a function and its derivative? Do you see how if we take the derivative of the denominator, we get the numerator? So that's where you recognize, you go, oh, I see a function and I see its derivative. I think I'm going to try a u substitution, right? And that's what you want to do. So what we're going to do then is say let u equal, and then we have to figure out what we want to set u equal to. Well, the good news is you're generally going to set it equal to the function. So remember we said we found a function and its derivative. Set u equal to the function that we're looking at. So in this case, that's 6x squared plus 4x plus 1. Okay. And when we do that, if we take the derivative of u with respect to x, then what we get is, in fact, let me put this on a different line. So that means that the fraction du dx is equal to the derivative 12x plus 4 Okay, so does that make sense? We're taking the derivative of u with respect to x, so we get 12x plus 4, so that's our du dx. If we multiply both sides by dx, we get the following. So, and I'm just showing all the steps right now. Most of you will skip a couple of the lines that I write here, but this will end up being then that du equals 12x plus 4 dx. Now, technically, that should be in a parentheses. I'll go ahead and write it for now. I wasn't going to write it, but until everyone understands what we're doing, I want to write every step. And I should close that. So du dx is equal to 12x plus 4. If you multiply both sides by dx, we get that du is equal to 12x plus 4 dx. Okay? So if you're writing it in this form, I'll go ahead and show the way they do it. You can make your substitution, because notice we have 12x plus 4 dx right here, and we have 6x squared plus 4x plus 1 in the denominator. So this whole big complicated integral that we started with becomes the integral of du over u. See how much simpler that is? It's basically the integral of 1 over u, which hopefully you're going, oh, I know the integral of 1 over u. It's the natural log, right? Because that's one of the ones we learned, what, last week sometime, I think, right? So that's the idea, is you're trying to come up with a substitution that substitutes into this and accounts for everything. You can't still have x's sitting around. Between your u and your du, you have to account for all of the x's in one way or another, right? Sometimes you'll get into more complicated problems where you have to substitute again, but you have to have turned all of your x's into u's. You can't have both u's and x's in the problem at the same time. It's not going to work, okay? So here, I'll just skip over to here because they have it written really well. So this big complicated integral that we started with becomes the integral of du over u, but we, like I said, we learned last week that the integral of 1 over u is natural log of absolute value of u, and then we have the plus c. So see how it all becomes this right here? But here's the issue. The original problem was not given in terms of u, it was given in terms of x. So we have to put the problem back in terms of x. And you might go, well, that sounds silly. Why did we take things that were in X, turn them into U, and then now we're turning the U's back into X's? And the answer is because look how much simpler the problem got when we did it in terms of U's. The problem became very easy to see how we are supposed to simplify things. That's why, because it allowed your brain to see the problem in a simpler way that we could move forward. And then the last step is just substitute back in. So see how this U becomes a 6x squared plus 4x plus 1? But remember, that's just our original substitution. We said that U is equal to 6x squared plus 4x plus 1. So at first, we turned 6x squared plus 4x plus 1 into a U. And now at the end, we're turning the U back into 6x squared plus 4x plus 1 in the absolute value, because that's the formula. And then we have the plus C. Don't forget the plus C on the end of the problem. Okay? Excuse me. So that's how we do U substitution. And that's kind of the thing, you know, you'll have different problems that are U substitution problems, but they all work mostly like that. Occasionally there's a few extra steps you have to do, but mostly they work like that. So let's look at this one. Let me walk you through this one. Both of these sections we're doing today take a long time to like write out. So I'm just trying to show you in the book so I can show you what all these steps are, because I know it's confusing, but hopefully you'll sort of get it. So here we have the integral of x over 3x squared plus 5. So this time you're looking at it and you're going, well, he said that we should be looking for a function and its derivative. And you go, well, I see a 3x squared plus 5, but the derivative would be 6x, and I don't see a 6x anywhere. I just see an x. Actually, technically, the derivative would be 6x dx. And you go, but I don't see that. I just see an x dx. Well, the key is we can make it work, but there's a little bit of effort we're going to have to take in order to make it work. So does everyone understand? The derivative would be 6x dx, but we don't see a 6. We see x dx. So we're trying to figure out what to do about that. So we still start off where we let u be equal to the function, 3x squared plus 5, the function that we're dealing with. So du dx is equal to 6x, like I said a second ago, so du is equal to 6x dx. Well, that's great, but how am I supposed to substitute it in here when we don't have 6x dx? And the answer is we make an adjustment. So see how we have du is equal to 6x dx? Well, we don't want 6x dx, we want x dx. So what we do is we divide both sides of this equation by 6, giving us x dx equals 1/6 du. Well, that's good because we do have an x dx, right? That's what our numerator is in the problem. We have an x and then a dx. So now we can make that substitution. So the key is you sometimes have to do a little bit of accounting here, and you have to account for the fact that, like, well, 6x dx doesn't exactly fit the thing that I'm trying to use in this function, but x dx equals 1/6 du, that does fit, right? The x dx does. So you can see what they've done here. They've turned the 3x squared plus 5 gets turned into the u. That's that substitution. And the x dx, well, that we just figured out right here that x dx becomes 1/6 du. And what we generally do to make the problem just a little bit easier to manage is we pull the 1/6 out front of the integral sign. That's how it ends up out here in front. And then look what we're left with right here. The integral of du over u. How easy is that, right? We just did a problem like that. That ends up being the natural log of u plus c. So then you substitute your u back in terms of your original substitution, which right up here we said we wrote u is equal to 3x squared plus 5. Well, that's what we're doing right here. We're turning this u back into 3x squared plus 5. So you use that same substitution, and I encourage you to write it down. A lot of students make the mistake of not writing down the substitution. They make the mistake of not writing down the substitution, and like, trust me, this happens all the time in math, but especially in calculus, it'll just mess you up. Where students go, "Oh, I'm gonna save time by not writing something down," but it ends up costing you time because you're going to make mistakes way more often, and those mistakes cost you way more time than a couple seconds of writing the problem down. So whenever you make this U substitution in your head, don't just hold it in your head. Write it down on the paper that you're working on. Trust me, it's going to move you through the homework faster than if you try to just think about what it is. Lots of students try to do that, and it basically doesn't really work unless you're an ace at these, but you're not going to become an ace at these without writing it down. So, if you become someone who does these all the time, then sure, you'll get good at them where you don't have to write every single step. But for 99% of students, you will end up way ahead if you just write your substitution down. So you write it down and you make the substitution in the beginning into U, and then down when you get down to here, you look back at that line and substitute right back in to what X is. Right? So it's a really good idea to have it all written down, and then you've got your final answer, right? So how come they were able to go from absolute value to parentheses? Can you always just do that? No, but if you think about 3x squared plus 5, that's never negative, right? When you square something, it becomes positive, and then you add 5, it still has to be positive. So that's why they were able to drop the absolute value, because that function can never be negative in the first place. So then you simplify everything down. And then they check it in the end by differentiating. Remember, it's really convenient when you want to check your work for an anti-differentiation problem. What you need to do is differentiate the work that you did, and if you get what you started with, then you're good to go. Okay. So, like I say, you'll see this pattern. Some books call this they call it the logarithmic derivative. It's basically where you see the function in the denominator and you see the derivative in the numerator. Then you know it's going to take this form of those last couple problems that we were just looking at. Okay, so before I dive further into that with the strategy, let me go ahead and take roll. right, the only person I'm missing is Trey B. So Trey B, if you're in here, let me know so I can make sure you're accounted for. So there's a question here. Will this practice test have the answers so we know if we got it correct? The answer is no. So I know that might seem kind of strange, but I have found for certain classes, and this is one of them, if I give out a practice test that has the answers, most students just kind of look at it and go, oh yeah, I would have got that. And then they end up doing really poorly on the test. So I don't actually give the answers to the practice test. It's supposed to be an exercise in you working through that and then using the resources that you should be using to prepare for a test. So you are more than welcome to take the practice test to the tutoring center, work on it with the tutors, have them figure out if you're doing it right. Also, you can form study groups in this class, get together with each other, compare answers. You can do it online. If you want, you can do it in person, whatever you think, so that you're comparing those answers and actually working on the problems and trying to work your way through it, rather than just being given a test, like a solution set where students just, I mean, I've seen it in action. They just kind of look at it and go, oh yeah, that I would have got that right. But then when they take the problem on the test, they don't get it right. So no, this practice test will not have answers. I have found that it actually works better for students if I don't get them the answers. I know it's easier if I give you the answers, but it's not as effective a learning tool if I give out the answers. But you are welcome to work with whoever you want in order to work on it, and you can come together to figure out if it's the right answer or not. Okay. Okay, with that said, let's see where we at. Okay, so here we have a strategy for substitution. How do we know which part of the integrand to let u represent? So I kind of gave that away a little bit. It's when you're looking at the u substitution, you're looking for a function and its derivative. So the part that ends up being the function is generally the one you want to be the u, and the part that is the derivative is going to be substituted for with your du. Okay, so they give you a little bit of a hint here. They say for a quotient, let u be the denominator. That's because most of the time in that situation, it comes from taking the derivative of a log, and you have the function in the denominator and its derivative in the numerator. So they give you a couple of keys here. They're not always the right answer, but usually those things are along the right lines. So let's look at this one. This is of a different form than we've looked at so far. So let me just kind of, rather than type all this up, which takes a while, let me just walk through these. And then if you totally understand the problems in the book, then you should be fine when you get home, because there's only a few different types of these problems you're going to do. So if you can get to where you recognize them, like when you're doing the homework and you go, oh, this is like that one that has a fraction. Oh, this is like that one where it's an exponent. This is like that one. Then what you can do is find the similar problem in the book and go, oh yeah, he talked about this during class, so you should totally understand the problem. And then you just sort of use that same technique on the problem that you're looking at. So in this case, we have 3e to the 3x plus 7. So think about how that works when we do the chain rule, right? So let's take a look over here when we're doing the chain rule. Say we've got, say f of x equals e to the 5x minus 6. Then the derivative, how would the derivative look? The derivative, well, we get this function back, right? Because it's going to be e to the 5x minus 6. That's just the outer derivative. The derivative of the outer function is just itself because it's an exponential. But then we have to use the chain rule, which tells us to multiply by the derivative of the inner function, which in this case is 5. So see how we get, and then normally we would just then write this as, actually I could write it right over here. we would write this as 5e to the 5x minus 6. So do you see kind of a pattern here? We're seeing that again. We see the function occurring in the exponent, and we see its derivative occurring as the coefficient. So that's kind of, that's giving us a hint into how, oops, trying to grab that window and I accidentally minimized it. Windows is so weird. I have to be so careful. If I don't do it just right, it does weird things with the, there we go. It does weird things with the, like it'll pop it to fit the whole screen and stuff. It does weird things. Okay, see how that's similar to what we're doing? 3e to the 3x plus 7. So see how the function is occurring in the exponent. And then if we take the derivative of that, we'd get 3 dx. Well, here's our 3, here's our dx. So everything is there for our substitution. So that's why they say, okay, well, let's let u equal 3x plus 7. The u is generally going to be the function, and then the rest of it gets cleaned up when you take the derivative of the other pieces. So du dx equals 3. Multiply both sides by dx. You get du equals 3 dx. So u is equal to 3x plus 7. Du is equal to 3 dx. But in this case, yeah. So we take our function. You pull the 3 out front. Then we've got our... we've got our 3e to the 3x plus 7, 3 dx. So now they've pulled the 3 into the end. But notice this is our du piece right here, the 3 dx. That becomes our du. And the e to the 3x plus 7, that becomes our u. So now what are we left with? The integral of e to the u du. Well, that's another really easy integral to calculate. The derivative of e to the whatever is just that thing. So when we take the integral of e to the u du, we get e to the u plus c. There's that plus c that we always have to remember to put on the end. And then we just we substitute back in terms of x to get e to the 3x plus 7 plus c. Okay, so it's another one of those forms you're going to run across regularly. This is just a more advanced version of that problem. Except here, notice that our function and its derivative are a little bit more complicated. So 5x squared minus 2, that's the original function. And what's the derivative of that? That would be 10x. Well, we don't have 10x, we have 4x, but they just play that game that we did where you just adjust for that, right? You just make an adjustment in your substitution. Okay. All right, here's another version that is different that we haven't seen yet. This one looks really complicated. This is actually very similar to the one that I started off with. Right, remember this one, right? Up here where we had a function raised to a high power and we took the derivative of it. So you get this really complicated looking thing. But if you're used to watching these, you go, oh, that's actually not too complicated. I've got my function. I've got its derivative. So I think I can go through and get all the pieces in there. That's the kind of problem we're looking at now. So you look at this and you go, oh my gosh, that looks crazy. But when you look at it, you go, okay, we've got 9x squared plus 2x plus 7. That's the function. When we take its derivative, we get what? 18x plus 2. Well, 18x plus 2 is twice 9x plus 1. So as long as we make that adjustment that they make right here, then you're good. And you can go through and make that substitution. So the key is write out your u substitutions. Remember, the u is always the full function that occurs in the problem. And then you're going to use the du to substitute for the rest of it. And then we get it down. Like, look, this piece over here on the left looks crazy complicated, right? You're like, oh my goodness, how am I supposed to wrap my brain around that? But look, once you make the substitution, look how much it all simplifies. The integral of u to the 8th times 1/2 du. And then you just bring the 1/2 out front. It becomes 5 times the integral of u to the 8th du. That's pretty easy to deal with, right? And then you do the antiderivative. So what did they do? They increase the exponent by 1 and divided by that new exponent. So you get this, and then you just make the substitution back in terms of u, which is 9x squared plus 2x plus 7. So not bad, right? It looks really scary. This thing over here looks super complicated, but it's actually it's not very difficult if you understand how to set up your substitution. If you can do that, then you're good to go, right? You'll be fine. All right, here's another one looking kind of complicated, but it's not too bad. But we can see, what do we have a function and its derivative occurring, or approximately its derivative occurring? We've got 8x to the 4th minus 5. So what would the derivative of that be? That would be 32x cubed. Well, we do have an x cubed, but we're off by a factor because we have 32x cubed, and we're trying to get to x cubed. Well, that's okay. That's that factor we can always adjust for the way they do right here. You just divide by the amount that you need to get the substitution to fit right. You're just basically making an adjustment in how you write that. So again, they take something very complicated, and then one of the keys in calculus when you see a root symbol is to write it in terms of the exponent, the fractional exponent that it represents. If you can remember to do that, then you won't really get stuck on problems like this. People get confused when there's a square root, or in this case, a cube root. But if you write it in terms of rational exponents, you just kind of go, oh, okay, that's actually not too bad. Okay. So here's where we run into an issue. So this one I'm actually going to write out by hand because this one gets a little complicated. So I mean, I'm not going to write it out by hand. I'm going to work through the problem because I want to make sure we talk about each individual step to make sure we appreciate this one. So this is the, give me 1 second here. Let me look something up. Oops, that's not what I wanted to do right there. There we go. Okay, so right now it's making the integral symbol kind of small. The program that I use does some different stuff with that. So depending on how you want to represent it. So I don't want to take the time to like fix it, but imagine this integral sign is bigger than it is. So let's look at the problem that we're looking at, where this becomes the integral of x times the square root of x plus 3 dx. So this is example 7 from the book, okay? So we have a little bit of an issue because look what happens when we go to make our substitution. And at that point, we're still not even sure because remember how I've been telling you to look for a function and its derivative? Well, we don't really have that here, right? We have x plus 3, but the derivative of x plus 3 would not be x. So we have this other x left over that we're not sure what to do with. Like, what am I supposed to do with that? So let's go ahead and start to work through how this problem should work. So what we want to do is say we want to let u equal x plus 3. Oops. Let u equal x plus 3. Okay, but see how if we make that substitution, we're still left with this x, and how am I supposed to get my hands on that? Okay, so let's figure out what du would be. So du, so the fraction du dx would be equal to 1, because the derivative of x is 1. So that means we'd have du is equal to 1 times dx, which is dx, right? That's not helpful. That's not going to get us the substitution that we need, because we'll substitute x plus 3 in for u, but what am I supposed to do with this x out here? It's left over. We can't have leftovers. We can't have u's and x's existing at the same time in the problem. So what are we supposed to do? Well, what you have to do in that case is see if your original substitution, u equals x plus 3, can be of help to you. Is there a way that we can use this in order to substitute for this x right here? And the answer is yes, we can solve for this x right here. So if I take the original substitution, u equals x plus 3, and I subtract 3, I get u minus 3 equals x. So now if you notice, we have everything that we need, because the x plus 3 can substitute in here and give us a u, and then the x out here we just decided was equal to u minus 3, so we can put a u out there. So this integral that we're trying to do after we make the substitution becomes u minus 3 times the square root of u. And then we've got our du, right? Oh, now it's really messing up the integral. Let's see. Okay, so see how this integral has become this one down here? The square root of x plus 3 became the square root of u because of this substitution right here on the top. The dx became the du because of this substitution we got on the second line. And the x became u minus 3 because of this substitution from down on the bottom. Right? And that might seem like there's a lot going on, but that's okay. Now we can just sort of deal with the algebra involved and see what we end up with. So if we take this piece, I'll show you some algebra here. So remember I said a minute ago we should rewrite the square roots of things as rational exponents? That's what we want to do. We're going to rewrite this as u to the 1/2. The reason that we do that is because it makes the exponent rules for calculus apply much more directly, right? So u minus 3 times u to the 1/2 is the same as u minus 3 times the square root of u. Those are equal to each other. And now if we distribute the u to the 1/2 in, I'm going to get u to the 3/2 minus 3 u to the 1/2. Let's see if I got that parsed correctly. I did. I got it. Okay, good. So u to the 3/2 minus 3u to the 1/2. Okay. All right, is what that looks like. Now this should be easy to take the derivative of. Right? We've sort of done the hard piece. So now I'll jump back to the example where they have it all written out. So we're here, u to the 3/2 minus 3u to the 1/2 du. So we break it up into two separate integrals, bring the 3 out front. So this is where you're doing that anti-differentiation that you did in 5.1. You're just anti-differentiating both pieces. So you raise the exponent by 1, so 3/2 goes to 5/2, but then you divide by 5/2. Over here, 1/2, when you add 1, becomes 3/2. Divide by 3/2. Go through, simplify your coefficients. You end up with this answer and the plus c. Okay, so I know it looks super complicated. It looks way fancier than it is. As long as you're just following that u substitution, it's going to come out nicely, right? Okay, integrating the exponential function. So that one's not too bad either. If you've got e to the ax dx, you'll end up with e to the ax over a plus c. I almost think you shouldn't even memorize these, because if you just think your way through that u substitution, you're going to learn it so much better. All right, but there's some examples on doing that piece. Okay, so that's largely what you're going to see for that section, and we can see that in the homework. That's largely what you're seeing here, right? You're seeing, actually, there's not even that many questions. Oh, I guess there's more than I thought. 13. Move this back over so you can see. So we're looking at, exponential functions, just like what we just did. Here's one similar to what we just did. We did, what, x times the square root of x minus 3. This one's x times the square root of x minus 5. Your number will be slightly different, probably. But same situation. Look, here's a function. There's a version of its derivative. Here's a function, part of its derivative. A function, part of its derivative. So you're seeing that again and again and again in these problems, where it's a function and then almost the derivative, sometimes exactly the derivative, but usually you have to scale that. You have to accommodate for that little bit of difference in there that just changes it by a factor of whatever to make it fit right. So make sure you watch the videos for that and for those. And then remember, there's only like 4 different types of those. So use the ebook to find examples that fit nicely for what you're trying to do. Like if you're doing, if you're doing this one where it's, here we have a polynomial to a power. Find the polynomial to a power one in your book and like make sure you understand it, and then try to do that for your problem. Here we've got one where it's a fraction, where you've got a function in the denominator and its derivative in the numerator. Find one like that in the book, make sure you understand it, and then do it for the problem that you're working on, right? So that it might, like here's another version. This is one where you've got your function. It's basically a polynomial to a power, and we're working backwards through it. The same ones come up again and again and again. So the trick is to find one like the one you're doing, make sure you understand it, and apply it to what you're working on. Okay, so that's 5.2. Okay, and we're actually going to take a quick break, like 5-minute break, and then we'll meet back here at the top of the hour. So feel free to stretch your legs, get a drink, something like that. We'll be back in like 5 minutes, okay? Okay, welcome back, everybody. Let's get going. So 5.3 is the definite integral. So let's take a look at some of those problems. So the first thing you notice when we see these types of problems is our integral sign looks different now, doesn't it? Now it's got these numbers at the top and bottom. That is the number one way that you will tell the difference between an indefinite integral and a definite integral. So the indefinite integral does not have these numbers at the top and bottom. The definite integral will. Okay, so when you don't see the numbers at the top and bottom, like you saw in 5.1 and 5.2, where there's no numbers at the top and bottom, that means you're finding the antiderivative. That's where you figure out what that thing has, that function as its derivative. You put the plus c on the end, all that stuff we've been doing for the last two sections. Once you see these numbers here, we're now talking about the definite integral, which is an area, which is different. So it seems so weird that like we would use almost the same notation for these two very different ideas, but we're going to work through that and make sense of it today. Okay. Right. Okay. So let's take a look in the book, the ebook. Okay, so like I mentioned, the fundamental theorem of calculus, but in this book they jump into it kind of early, so it shows up a little bit earlier than usual. Let's see. There should be in here. Where was that picture? Sorry, I'm trying to remember. This book sometimes does things very differently, and I'm trying to remember how exactly they're different. Because, right. Okay, so we kind of give you, this is kind of a brief overview. This is leaving some things out. If you ever take like a engineering calc course, you'll spend a lot more time developing this part, but we just sort of move through it rather quickly. So basically what we do here, we have this fundamental theorem of calculus. And what this is a thing that seems kind of weird, like this thing in the middle, you're like, what am I looking at? So what this says is that if f of x is a continuous function on a closed interval from a to b, so that means the x interval, right, the x-axis, you're on an interval over two different x values, so from a to b. Whoops, let me close that. Okay. And capital F of x is the antiderivative of f of x. So capital F of x, when you take its derivative, you get lowercase f of x. If you have little f of x and you take its antiderivative, you get capital F of x. Okay, so we have that relationship. We have two functions. One is the derivative of the other one. Then the definite integral of f of x from a to b is given by the following. The integral from a to b of f of x dx. And the way we actually evaluate that is by taking the antiderivative and evaluating it at a to b, which means this. We take f of b minus f of a. So this is where b is the right endpoint of our interval, and a is the left endpoint of our interval. They don't have a good picture in this book. I forgot they don't have a good picture in here. But basically what this is saying is you still take the antiderivative like you did before, except before we would take the antiderivative and put a plus c on the end. Now we take the antiderivative, and you don't have to worry about the plus c. You input the right endpoint into the function, and you subtract what you get from the left endpoint when you put it into the function. This actually gives you an area under the curve, which seems strange, and you kind of go, why would the area under the curve tell me anything? But it does. It just, that's part of what we're skipping over here, is that like it, like in an engineering calc class, we would take almost an entire period just covering that connection. We don't really have time in this class to do it. Plus in this class, you sort of skip over those steps a little bit. Basically, you just need the takeaway. How do you calculate these things, right? And it represents the total amount accumulated by capital F of x as x increases from a to b. The number a is called the lower limit of integration, and the number b, the upper limit of integration, okay? So like we just mentioned, how do you tell the difference between an improper integral, an indefinite integral and a definite integral, whether it has those endpoints on the integration symbol or not, right? The definite integral has those because you're actually calculating a number. Up here, you don't. So when you take a derivative, when you take an integral that looks like this with no endpoints, you should end up with a function, and you should add a plus c on the end. When you take the definite integral, you should end up with a number. Okay, so that's really helpful to remember. What do they look like so I know which one I'm doing, and what am I supposed to end up with? Up here, we end up with a function. Generally, we're going to tag a plus c on the end. Down here, you end up with an actual number that represents the area under some curve, right? Which accounts for the accumulated value of whatever that is that your accumulated amount of whatever it is that you're trying to study, all right? So you can see here, when they take the indefinite integral, notice how they end up with a function right here, and there's a plus c on the end. So you start with no endpoints, you end up with the antiderivative, and you have a plus c. Down here, they've got those endpoints, and notice what they end up with is a number, right? That's an area, but it's a number. So that's how you like, before you do the problem, like, predict for yourself. Should I end up with a function or a number? And then check it to make sure that it's right. So then we end up with all these properties that look kind of overwhelming, but they're actually really not, they're not, like, once you understand them, they're not as fancy as they seem. It's stuff we've kind of already done. This first one allows us to pull a coefficient outside of the integral. Okay, that's really convenient, right? That allows us to simplify the integral itself. The integral from a to a f of x dx is equal to 0. That means that the interval over, like, notice that our start and end points are both a. That means the interval over which we are finding the area has 0 width. So think about a rectangle. If someone told you that, well, I have a rectangle that is 10 feet long by 0 feet long, well, then what's the area of it? 0, right? So if something has 0 width, which is what we have because our integral has 0 width here, it goes from a to a, then the overall integral will be 0. That one doesn't come up very much. It's important that you get your limits of integration in the right spot. The left endpoint should be on the bottom. The right endpoint should be on the top. If you do it backwards, you end up with the negative of the value that you meant to calculate. And being off by a negative is a big deal. If you go to the bank and they have your bank account off by a negative, you're probably not going to be too happy with that, right? And they go, oh, well, we had the right number. We just had the wrong sign in front of it. Isn't it going to make you feel any better about it, right? So that sign's really important. Number 4 says we can break up integrals the same way we do derivatives, where we can break them up with the plus or minuses into smaller pieces and calculate those terms individually, right, which is convenient. Okay, the integral from a to b, f of x dx. This says we could break our interval up into 2 smaller intervals. So overall here we've got the integral from a to b. This says we could slice it into 2 by adding a c, where we take the integral from a to c and then from c to b, and we end up with the same thing, right? So nothing too fancy there. Okay, so let's see how this works in action. Let's actually see this taking place. And you like once you get the hang of this, you'll go, oh, okay, I see what's going on. So we want to evaluate the integral from 3 to 5 of x squared plus 3x minus 2 dx. Okay, so the first thing they do is say, well, let's break this up into smaller terms. The integral from 3 to 5 of x squared dx plus the integral from 3 to 5 3x dx minus the integral from 3 to 5 2 dx. So it's just what we did with polynomials before. Remember when we were taking derivatives of polynomials and we were just taking the derivative term by term? That's what we're doing here. We're just taking the integral term by term. All right, we're just splitting it up piece by piece. Notice that each piece ends up with a dx in it. It's not like the one at the end just gets the dx. And then what's this line here? This line means we're going to evaluate it at these terms. So that's why if you take the antiderivative of x squared, right? So you increase the exponent by 1 and you divide by that exponent, we end up with x cubed over 3, but we want to evaluate that at 3 and 5. So we plug 5 into here and we get 5 cubed over 3. And we subtract from that what we get when we plug 3 into here, which is 3 cubed over 3. So this bit in parentheses right here, that's what we get from simplifying this piece. We're taking this antiderivative and we're evaluating it at these two endpoints and we're subtracting them. And then we just keep doing that. So take 3x over here in this second integral. Increase the exponent by 1. Remember, since there's no exponent, it's like an invisible 1 there. So the 1, when we add 1, becomes a 2, and then we divide by 2, so we end up with 3x squared over 2. But we're evaluating that from 3 to 5, so then the 5 gets put in here, and the 3 gets put in here, and then we're going to subtract the 2. And then the 2x piece is pretty straightforward. You put in 2 times, if you take 2 and integrate it, you get 2x. So when you put 5 in, you get minus 10, and then it's going to end up being plus 6, right? So then you just add all those numbers together, and you end up with 158 thirds. That's your exact answer. That is the value that this integral evaluates to. Okay? If there's any questions, feel free to ask. I'm just trying to really point out these examples so later when you're looking at these examples, you'll know exactly how these steps worked. So please ask if you have questions. Oh, then we have the definite integral and substitution. This can be confusing, and there's two different ways to do this. I prefer to use the way that is the less popular way, but I find just makes a little bit more sense. People try to do this other way, and it works. People use it perfectly fine, but you have to keep track of a couple things. I find it's easier to not keep track of things, but like I say, most people prefer the method that I don't prefer. So here we want to evaluate an integral. Let me make this a little bigger. We want to evaluate an integral, and it looks like we're going to have to use a u substitution here in order to do this. But notice how our endpoints are 4 to 10. Well, those are 4 to 10 in terms of the variable x. Then we go and substitute things in terms of u, which is different. But then what happens with those endpoints? So the key is if we make a substitution where u is equal to x minus 3, we have to, one way that people do it is you have to convert your endpoints to be in terms of u's as well. Okay, so you can see what they do here. See how this becomes the integral from 4 to 10 of 1 over x minus 3 dx, and it becomes the integral from 1 to 7 of 1 over u du. And you go, wait a minute, where did 1 and 7 come from? How did that work? Well, the answer is you take these numbers, your endpoints, and you plug them into your substitution. So u is equal to x minus 3. So our original endpoints were 4 and 10, right? So these are x values. So if I take the 4 and plug it in here, 4 minus 1 is 3. That makes my new u value 1. So see how the lower endpoint now is 1? Because we sent the x values through the u substitution, and they got turned into new u values. So what happens with 10? When we plug 10 in here for x, 10 minus 3 is 7. That tells us our u is 7. And sure enough, that's our upper endpoint of integration now, is 7. Okay? Does that make sense? You have to send your x values through that substitution to translate them into u values, since we're doing things in terms of u. Now, the way I usually do this is I don't transfer those numbers. I just turn everything back into x's. But you don't have to do it. It's really the same thing. It's just two methods to do the same thing. So if you're going to turn everything back in terms of x's, then you can leave those endpoints the same. If you want to just evaluate here once you turn it into u, the way they do in this problem, then you have to transfer those endpoints, that upper and lower endpoint of integration. They have to get turned into something. Okay? And then you can see, again, this bar tells us that we plug in the top value and subtract what you get when you plug in the bottom value. So natural log of 7 minus natural log of 1 is natural log of 7 minus 0, because the natural log of 1 is 0, right? Okay. So you can see in this example, they're kind of doing the same problem, except they're doing it the way that I described, although they're actually making it a little weird. But it's basically the same thing. Notice how they're just saying, we're not going to choose these endpoints, but they're specifying that they're x values. So you remember you have to turn this back in terms of x's. So see how they took the integral and they had it in terms of u, and then they turned them back into x's. That's my preference. It's a little strange that they keep writing x equals, but I think that's so they don't confuse the new student who's just starting to do these, as far as like, wait, are these x's or u's now? It can get confusing. So either one of those ways we just looked at this problem, they're both right. They both are legitimate ways of doing the problem. I prefer the second way, but I'll tell you most people prefer the first way. And you can see it's a little bit shorter here, right? A little bit short, just slightly shorter. I mean, I'd almost say that's because they did some of the work up here of actually transferring those endpoints. But, you know, it doesn't matter which one you choose, which way to do it. So let's look at some of those problems from class here. So for the, so next time we'll take a look at so we looked at the definite integral. Oh, that's actually what I was going to get to today. So I think we're going to get a little bit into 5.4 today. I think we can do that. So for instance, like on the homework here, what are you going to do? You're going to take the antiderivative of this function right here. You're going to evaluate it at 1. And then you're going to subtract what you get when you plug 0 into the antiderivative. And then what you get will be your answer. Right? That'll be what you end up getting. So let's do this. Let's take a look at 5.4. Watch the videos for 5.3. I think you'll be good. Let's see. Yeah, we've got substitution, definite integral, fundamental theorem of calculus, integration by parts for the definite integral. Yeah, we've got all these pieces. Whew, this room's getting warm. Okay, so you heard me refer to a few times about how the definite integral is giving us an area under the curve. And you can see right here, they're coloring in an area underneath the curve. So that area under the curve ends up being very important, right? So we're getting into 5.4 now. The question is, how do you calculate that area under the curve, right? So let's talk about this. So before we start computing areas, we need to have some understanding of what area is. Intuitively, the area of a region is a measure of the size of the region. It is something that can be defined. For example, we can have the area of a rectangle, the area of a triangle, the area of a circle, right? These are things that most people sort of understand. But the problem is, you could imagine, I've mentioned areas under the curve so far. Well, how would you measure the area under this curve? You can't really use any of the formulas that you're used to, that you've had since, grade school, of area of a rectangle, area of a triangle, area of a circle. None of those are going to help, because this curve has its own special shape, and then the next problem is going to have a slightly different curve. So how is it that we can go through and do that? Here's basically how it works. This is going to sound weird at first, but once we start using the power of calculus, then we can leverage basically the power of limits to save the day. So the way that we approximate the area under the curve is with rectangles. So we start putting rectangles in there. So notice how up here in this picture, we've got the integral from a to b. It's not coincidence that we're using a to b here. And remember how we were using a and b in our definite integral for the upper and lower endpoints of integration? That is not a coincidence. That is because that definite integral is being calculated over the closed interval from a to b on the x-axis, right? Not a coincidence. So what we do is we take this area here and we say, let's approximate it using rectangles. So your worst approximation is just one rectangle. Let's just take one rectangle. We'll approximate the area under that curve, right, for this picture. So you just make one big rectangle out of it. Well, that's obviously not very good. We're missing some area over here. We're counting some area over here that we shouldn't be. So we say, okay, what if we break it up into more rectangles? So in this case, we're using 4 rectangles to approximate this area under the curve. And hopefully by looking at it, you can go, well, that's a little better. We've got a little extra area here still in these corners. We're missing some area on these corners. So it's still not perfect, but it's better than that first one. And that's what we keep doing, is basically we use these smaller rectangles to approximate the area. Now, how do we do that? How do we know the area of each of these small rectangles? Well, for one thing, what we do is we keep the width of each of these rectangles the same. And the way we do it is we take the area from A to B and we break it up into n rectangles. So let me show you here. If we have area under curve from A to B. So we've got the area under the curve from A to B, and we want to use, I can't see my typing here. We want to use n rectangles. So we've got an area from A to B. We want to have n rectangles in there, and we want them all to have the same width. Well, what's the length from A to B? So our length from A to B is, well, use subtraction to find the difference, right? So that's going to be B minus A. So the length from A to B is B minus A. And we're breaking that layer up into n rectangles, n equal with rectangles. So the width of each rectangle is the fraction b minus a, that's the width of your interval, divided by n, that's the number of rectangles that you're using. So it's b minus a over n. The width of each rectangle is b minus a over n. So it's a really easy calculation. B minus a is the width of your interval. Like if we look at that picture again, oops, that's the wrong book. Here's the one I want. Right? You can see that. What's the distance from B to A, or from A to B? It's B minus A. That gives you this distance right here. And then if we divide it by 4, that gives you the width of each of these rectangles. Right? So if we want to use n rectangles, you just take the width of the whole thing and divide by n the number of rectangles that you want to use. So it's an easier calculation. But how do we get the height? How do we get the height of these rectangles? Well, if you'll notice in this case, see how the rectangle on the left top endpoint is touching the graph? That determines how tall the rectangle is. But the nice thing about that is that's a function value. So if I wanted to know how tall this rectangle was, well, I would just use my function f and evaluate it at a. So f of a is the height of this first rectangle. And then for this one, I would take f and I would plug in whatever this x value is right here. That would give me the height of this rectangle. Then I would take whatever this x value is, plug it into the function f, and it would give me the height of this rectangle. Then I would take whatever this endpoint is, plug it into the function f, that gives me this height. And you go, well, yeah, but how do I know what those middle ones are? Well, you're going to do it because you're going to break up that interval into a bunch of pieces, all of which whose width is b minus a over n. So you know exactly how far to move over for each new rectangle. Okay. So that's when they say the height is f of x 0. They're just saying, yeah, that's this endpoint. Plug it into the function. That gives you the height. And then you keep getting these endpoints, but when you plug them into the function, they tell you the height of the rectangle. Here you can see our b minus a over 4. We did it with n in general, but for this problem, there's 4 rectangles. So the width of each rectangle is b minus a over 4. Right? So now what you do is you add up the area of those rectangles, and that is an approximation for the area under the curve. Now, I know what you're thinking. You're like, that's a terrible approximation for the area under the curve. But the reality is we don't use 4 rectangles, right? Some of you might already be seeing where this is going. We use n rectangles, and what do we do with n? We take the limit as n goes to infinity. So as the number of rectangles goes to infinity, our approximation for the area under the curve gets better and better and better and better to the point where in the limit it becomes perfect. Okay. So we have you do a few of these by hand. This is always traditional calc class. You do a few by hand just so that you understand what's happening with these. These are called Riemann sums. But in reality, you're never going to calculate this by hand because one of the great things about computers is that they're perfect for calculating this kind of stuff. If those of you who ever learned a programming language, you literally could write this in a for loop just a few lines long, right? So while it might take you 10 minutes to do a problem where you use 5 rectangles on something like this over here, in 5 minutes you could write computer code to have it go through and do 100,000 rectangles for you. Right? Are you going to be able to do 100,000 rectangles by hand? No. So the computer is going to not only be more accurate than you can be, it's going to do it in a fraction of the time. It's going to do 10,000 rectangles before you can do 5 by hand, right? So we hand it over to computers and they do it. In fact, the very first computers, if you ever go back and you look at the very first computers that were, being used in World War II and stuff like real primitive computers, like, a computer that like doesn't even have enough computing power as like a calculator watch or something like that, and it would be the size of a building, right? The size of like multiple large rooms. Those early computers, this is literally what they were programmed to do. The very first programs were calculating these integrals because they could be used for really, help win the war, basically. So that's the kind of stuff they were doing. So again, this is one of those situations where we have you understand how this process works, but then in reality, in real life, when we have to calculate this stuff, you don't usually add up these rectangles by hand. You tell some computer to do it for you. Okay. And we can kind of see here. Here's an example. Using these rectangles, each has width 1. So they make this one kind of nice. We're going from 1 to 6. And we're using, use rectangles to approximate the area under the planar region of this function on the interval from 1 to 6. They want us to break it up into 5 rectangles. So we take 6 minus 1, the upper end point, minus the bottom end point. So that's where the 6 minus 1 comes from. Oh, they want it in 4 rectangles, sorry. Divide it by 4, that gives us 5/4. That means the width of each rectangle is 1.25. Okay, so you start at 1 here. So how do I know what my next endpoint is? Well, we know we're supposed to move over 1.25. So if I start at 1 and I move over 1.25, that gives me 2.25. That's my next endpoint. Well, what's the next one from there? Well, I start at 2.25 and I move over 1.25. That gives me 3.5. Right? Do you see how this is going? Then you're going to move over 1.25 again. That gives you to 4.75. Then you're going to move over 1.25 again. That gets you to 6. So now you have the endpoints of your 4 rectangles. 1, 2, 3, 4. Actually, they threw in the last one. This is one mistake that students make, is they'll actually accidentally calculate one too many rectangles, and then they're going like, wait, why is my number off? But notice how we're supposed to calculate 4 rectangles, but there's 5 values because they went all the way to the end. But if you plug this in, then you're essentially simulating a 5th rectangle that's outside your interval. You don't want to do that, okay? So then what do? Well, we go through and they calculate the height at each of these x values. So do these x values look familiar? Those are our endpoints. We start at 1, then 2.25, then 3.5, then 4.75. So we've established those are the endpoints of our rectangles. But remember, those are used to calculate the heights of here, of these boxes. So we take these x values and we plug them into the function, and we get the outputs. Those are the heights of the function. Okay? So then you get those values. Those are the heights. Each one is 1.25. So you take the width times the height, and you put all those together, and you'll end up with the area, adding up those areas, and we'll get the area under the curve. The one rectangle would give you 67.5. When we use 4 rectangles, we got 43.9375. But the actual area is 43.125. So you can see as you start adding rectangles, a lot of times your values will get much more accurate very quickly. Okay, so then you can see the formula we actually did, where we did it in general, b minus a over n. That's your delta x. What does delta x mean? Delta means change generally in calculus and science. So they're saying the change in x as you go over each rectangle, that change in x, delta x, is b minus a over n. That's the width of each rectangle. Okay, so then you go through and you add them up. This s sub n, let me make this bigger for you. The S sub n stands for sum, and it's the sum. The n tells you how many rectangles to make. So S sub 5 means find the sum with 5 rectangles. S sub 11 means find the sum with 11 rectangles, and you go from there, right? So basically what you're doing is you're taking the heights of the rectangles, and then using the distributive property, you multiply by the width of a rectangle, and that gives you the sum. This is called a Riemann sum. Okay? Well, then what do? Well, I kind of already gave it away. The limit as n goes to infinity means we're going to send the number of rectangles to infinity. which, like I say, even infinity is even big for a computer, right? But the reality is, for most integrals, once you go past like 10,000 rectangles, you're probably pretty accurate. So when we're doing things by hand, we will take the limit and send n to infinity. If you are actually doing this on a computer program, sometimes even 1,000 rectangles is pretty darn accurate. Okay, but it just depends on the particular problem you're trying to do. So, so there's kind of the picture we've been seeing again that keeps coming up. Okay, now we're going to relate area and definite integral, because it's not clear that these things are related to each other, but we're going to put them together. So let me kind of read this as it sums it up. We've defined the area under a curve that lies above the input axis and below the two vertical lines using the accumulated areas of rectangles. So essentially, remember what that means is we're finding the area under the curve, and a lot of times we say, oh yeah, the area under the curve. What we mean is the area under the curve, but above the x-axis, right? So like it would be this area in here, right? Otherwise, if it just kept going down forever, it would go forever. Also, you can run into a situation if your function drops below this line, then it's the area that gets trapped in there, the sort of the symmetric version, okay? So we've defined the area under a curve that lies above the input axis and between two vertical lines using the accumulated areas of rectangles. The word accumulated makes us think of the definite integral, and in fact, we draw the following relationship between area and the definite integral. So here's an important relationship. If f of x is a continuous, non-negative function on the interval from a to b, the area A, bounded by the function f of x, the x-axis, and the vertical lines x equals a to x equals b, is precisely equal to the value of the definite integral of f of x from x equals a to x equals b. That is, the area is equal to the integral from a to b of f of x dx. So that, I know that sounded really, really complicated, right? Like you might have to read it 5 or 6 times to really let each piece kind of sink in. But all they're saying is if we have, where's a good picture to use? Like here, they're saying if we calculate the integral from 1 to 6 and use the calculations that we used from the last section, where you take the antiderivative, we would evaluate it at 6 and subtract what you get at 1. That actually gives us the area under the curve. That's not at all obvious. And in this class, we don't really take the time to like really lay out exactly why that's true. So, you know, in a business calculus class, you just kind of believe us. You just trust us that it's true, that calculation, that weird antiderivative calculation from the previous section actually gives you the precise area under the curve. That's what this theorem is saying right here. This big confusing, you know, word salad bit, that's what it's saying. Okay? So they might say here, find the area bounded by this function and the x-axis and the lines x equals 1 to x equals 6. So when they talk about those vertical lines, they're just talking about these endpoints right here, right? The line right here and the line that would come down. They kind of show it a little bit better right, like right here at A, here's this vertical line. At B, it's this vertical line. So it'd be the area trapped in there. So it's just helping us define our endpoints on the x-axis is what that thing's really doing. Okay. Oh, so you can see what they did, right? Find the area bounded by the function. They gave us a function. They tell us from 1 to 6. So what do? We've got the area is equal to the integral. They gave us our endpoints of integration, 1 to 6, right here. Here's the original function they gave us, and then we slap a dx on the end. So actually, this setting up a problem like this is quite easy, right? They gave you the function, stick it in here. They give you the 2 endpoints, stick it here and here. The hard part is actually doing the integration. Well, that's what we looked at in the previous section, right? So here, the new thing that we're doing is setting up the problem, but it's not really the hard part, at least not in this case. There's times where they, you know, not as much in this class, but there's times where they leave a lot more interpretation for you to figure out. then it might be a little bit harder. But right here, they give you the function, they give you the endpoints, tell you, okay, go ahead and integrate it. And you can see what they did. They're finding the antiderivatives right down here, right? If we go down, we see the antiderivative of the term above it. So they're getting that antiderivative, and then they're evaluating it at 6. That's what all this is. And then they're evaluating it at 1. That's what all this is. And then they're just subtracting the 2. So it's just putting the previous section into use. Okay. So in this case, the point they're making here is that we're not really treating it as an area. It's already been interpreted as an area. We just have to figure out what that area is. So you're just told, calculate this thing. And then it's just like we did in the previous section, right? Yeah. What they're showing you here is, I kind of mentioned this a minute ago. We talked about area bounded between the x-axis and the curve and the vertical line. But what if your area was below the graph? So it was above your curve but below the x-axis. Basically, it starts to calculate that area as negative. So it would subtract this area. So it would take this area, subtract this area, and you end up with a negative. That's why you get, up here in this previous problem, you get -3/2 when you carry out this integral. From an area perspective, you'd go, well, how could you get a negative area? But it's because calculus treats this as negative. This area right here is negative. So just be aware of that when you have to calculate that. Yeah. That one's pretty straightforward. Yeah. You can also use Desmos to graph some of these if you're trying to figure it out. So they'll have, you're trying to figure out how these things work, trying to make sense of them. So just to kind of review, we've got our area under the curve. We're trying to calculate that. We are going to use the definite integral. So use the definite integral to make those calculations. So you'll have a few problems. Let's see. Let me double check. Which one's this? Is this 5-3? No, I want 5-4. Here we go, 5-4. So here they just give it to you as an area. They say determine the area of the region bounded by the given function, the x-axis, and the given vertical lines. So basically, you've got your function. So let's look at this one. Let's do this. Oops, that's not what I wanted. Where did Desmos go? Okay. Okay, so they're saying, oops, I don't want this one open anymore. So we're looking at, they want to know the area of the region bounded by the given function, the x-axis, and the given vertical lines. So they're giving us 3 square root of x. So let's go 3 square root of x. So there's our function 3 square root of x. Is it not? Uh-oh, did my screen freeze? Uh-oh. Okay, I don't know why I did that. Okay. Okay, it's working again. It froze for a second for some reason. Okay, so we've got our function. That's 3 times the square root of x. So what are they telling us? They're saying 3 times the square root of x from x equals 4 to x equals 9. Okay, so that means that we only care about from here to here. So let's make both of those orange just so I can be consistent. That means we only care about the area under this curve from 4 to 9. So let's get rid of the rest of it. In Desmos, the way you get rid of the way you define a restricted domain is with curly brackets. So I'll just say 4 less than x less than 9 and see how it cuts it down now. Whoops, let's just so I can show you the original. So see how when I get rid of the purple one, it's just showing us the part of the graph. Let's make that purple as well. It's just showing the part of the graph that's between the two endpoints they gave us, which was 4 and 9. So this is the area we care about right in here. They want us to calculate that. So they're saying determine the area of the region bounded by the given function, the axis, and the given vertical lines. So the way we interpret that area between the curve, right, we could take, 100,000 rectangles and put them in here, but the best way to do that is to turn this into the integral. So we would integrate 3 times the square root of x from 4 to 9 dx. You turn it into that definite integral and solve the integral, and what you get when you do that will be this area right here. It'll be this area that occurs. Okay, let's see. Those are kind of the same idea. So they're giving you different graphs, but they're things you know how to take the antiderivative of, right? This is one we could use U substitution on, right? We could use U substitution on those. Which one's this? Here they just write it in a slightly different way. Same problem, basically. Here you have an integral. This is giving you a person's investment is expected to produce a continuous stream of revenue R of the following. So this function is describing the continuous revenue stream, right? This is a business application problem. In dollars over the next 6 years, the accumulated value of this revenue stream from time equals A to time equals B is given by this integral right here. So it's the integral from A to B of R of t dt. Find the total revenue generated by this revenue stream over the 6-year period, round to the nearest cent. So, when you're using dollars, it makes sense to round to the nearest cent for many problems. So they've given you R of t. They've told you to take the integral from A to B of this thing, right, over a 6-year period. So over the 6-year period, over the next 6 years. Yeah, so they're just, it's a little, and they could have been a little more specific, but they're telling you like it looks like from 0 to 6, they want you to evaluate that integral. So do the integral from 0 to 6 of this function up here, dt, and that should give you what you want. This is a savings problem, same idea though. Here's one for fish in a lake. Here they're actually making you figure out your rectangles. So for this problem, they're giving you rectangles and say, so in this case, it looks like we have what? Use 4 rectangles. So notice you have 4 boxes, 1, 2, 3, 4 boxes. And then you've got a sum at the bottom. So you're breaking up 1/8, 1 to 8. So 8 minus 1 is 7, 7 over 4. So the width of each box is going to be 7/4, right? 8 minus 1, 7, divided by 4. So you'll start at 1, and then you'll go 1 plus 7/4 and figure out what that's going to be. Then you'll do 7/4 again to get the next x value, and then 7/4 again to get the last x value. Then you'll take you'll plug those values into your function over here, and that gives you the height of the of each rectangle. And you know the width, it's 7/4. We just calculated that. So then you can figure out the area, the total area, by multiplying the width times the height of each rectangle and adding those together. So like we looked at in the book. So let's see, did they give us one? No. Using 4 rectangles, the approximate area of the interval 1 to 8 is, then you're going to give your total value. Here I think they just want you to sum the f of x's and then multiply by the width. Because you kind of could do this either way, right? If you think about the distributive property, you could take each height and multiply it by the width. Or if you factor out the width, you just add up all the heights and multiply by the width. They're both correct ways to do it. One just has a few more steps than the other. Okay. Then we've got some more integrals to find. Yeah. So I think you should be able to get through 5.4 now. Okay, so you should be able to get through 5.4. Next time we will go over those last 2 bits. Is it 2 bits left or 1 bit? 5.5, yeah, 5.5 and 5.6 we'll go over next time. That'll close out the week. Then we'll start next week with chapter 6, and we'll go into those, okay? Anybody have any questions? I know it was kind of a lot to see all at once, but any questions? Make sure to watch those videos if you have any questions on how to do stuff. Okay, I'm not seeing any questions. So as always, I'm going to leave the Zoom stream open for as long as people want to ask me questions. So feel free to hop into Zoom and ask me questions. I'm going to shut down the YouTube stream. So see you all in a couple days. Come see me in Zoom if you like. Okay, thanks everybody. We'll